So we'll continue our discussion on distributed file systems. Last time I started talking about NFS, Network File System, which is the most commonly used distributed file system, most widely used distributed file system out there today. But that's not the only one. There are a host of others. So what I'll do today is run through a bunch of others that you may encounter at some point in time. We will not go into them at the same level of detail, but I'll provide the high level overview of how they may be different from NFS or some of the others that we are going to see. So we will start with Coda. We'll do that in a little more detail, and then I'm going to give an overview of a few others that you should at least know about. Okay, so we'll talk about Coda first. It's a distributed file system that started off actually as a research project at CMU, and CMU has the group at CMU that designed this has a long history. They have designed various different distributed file systems. Coda was a successor to another file system called the Andrew file system, which was actually commercialized. And then the research project continued, and they designed a second version of that file system called Coda, which is what we will look at. Okay, the main design goal for Coda was to design a file system that is suitable for mobile devices or mobile clients. Okay? This was back maybe 15-20 years ago, not today where everyone has a phone or a laptop, but even in those days they could see that mobile devices such as laptops were going to become more commonplace, okay, in the future, which is today. It is actually commonplace. And then the question was, if you needed a file system where your mobile device accesses data on some other server, what kind of features would you need to provide? So the main goal here was to provide support for what is referred to as disconnected operations. Okay, so the way a mobile device differs from a wired client is that the device goes from one place to another, and while it travels or in the course of being worked on, it may actually be disconnected from the network altogether. You may go on a plane. Okay, today even planes have Wi-Fi, but let's say that you are disconnected. Okay. So now question is, you need to get access to your data. What do? Okay, you can throw up your hands and say you are not connected to a network, so the file server is not accessible. You can't get access to data. That's not a desirable situation to be. So they designed Coda to say, how can you make these disconnection transparent or seamless? And the fact that you're disconnected shouldn't actually be something that inconveniences the user. The user should be able to continue their work on their data. Okay. So the way this works is you basically cache frequently accessed files on the mobile device. Okay. This is done automatically. You don't have to actually tell, you can provide hints to the server, but the server will learn your access pattern and cache the most commonly accessed files automatically on your machine. So if you're disconnected, you still have a copy of those files. You can continue to work on them. You can modify them. And when you reconnect, the system will automatically determine what files are modified, transfer them to the server. If the server saw some other users modify files, it will pull those files. Okay. So this is referred to as handling disconnected operation, which is really the key innovation that the Coda brought about. This is now widely used in a variety of contexts. Okay. If you see typical mail clients, okay, whether you use Thunderbird or Apple Mail, it doesn't matter. If you actually have the right preferences checked, it will automatically download a copy of your mail and cache it locally. So there's a copy stored on your inbox on the server, there's a copy on your device. So you disconnect, all your mail is still there. You can actually continue to send mail, except that it will be queued up and then the mail will be sent out, or you can modify, delete things, and later on it's reconciled. Okay? So that's the idea that Coda put out many years ago. Now it is prevalent in many applications as well as systems. Okay? So there's a file cache which takes into account user preferences. Always keep frequently accessed data in the file, and then learn what users are accessing, and then try to cache whatever you learned as well. Okay? So now the question is, how do you ensure transparency? How do you ensure that data moves back and forth without manual intervention? You could of course do all of this manually, before you go, you actually check out a copy and you make modifications and check it back in. Right? So you can do this, but you want to automate the process. Yeah, so we'll see the design of how Coda works. So this is a very quick overview of how file identifiers are maintained. So this is the metadata that you have in Coda. Typically what you have is, since files are replicated in this case, the servers are replicated, files are also replicated in caches or are copied into caches. You basically have a file handle that includes a server ID and a handle of the ID on the server. So it's the combination of the two, which is you have a 32-bit volume ID and a 64-bit handle. It tells you what server and what file on that server. Okay, this is how you are going to identify files, and we'll come back to that in a little bit. But let's talk a little bit about server replication. Okay, so first of all, the way Coda works is you can set up servers, and servers can replicate volumes. Okay, so you do no longer have a single server, because it is assumed that the servers may also get disconnected from one another and the system should continue to work. Okay. So you can think of entire file trees, some volumes being replicated on the server. So to ensure consistency, what is done is when there's connectivity among servers, you use read once, write all. If you remember the Gifford's quorum protocol, where I said if you want to read locally and ensure that your file is up to date, whenever there's a write, you should write to all of the replicas at the same time. This ensures that everyone has a copy. Rather than just writing at the master and propagating data, you're going to just write to all of the files at once, and then you read from any one that you have access to. Okay. Now, whenever there's a network partition, some servers will get disconnected from others. Okay. This is not the same as a laptop disconnecting and going off. Okay. That's also allowed and handled in Coda. There is a group of servers and they simply get partitioned because of network failure. Okay. So in this case, what happens is you allow each server to serve as clients as if nothing has happened. Clients can continue to perform writes. And then when the network partition goes away, all the servers are going to run what is called a reconciliation protocol and detect conflicts using what's called a version vector. So a version vector is simply for every file, you keep track of a version number. Okay? Every time you write to the file, the version number is incremented. It's simply an integer. Okay? And you keep a vector which tells you for that file what is your version number and what is the version number that other servers know about. Okay. So now if you have, let's say at some point in time, a file on one server that has a version number 221 and a file on another server that has a version number 112, what does it tell us? Okay, so it should tell us that there is a conflict. Okay, that the file, this is a single file, is out of sync, or is actually this is a write-write conflict, because it says that this group, which is there are three servers here, server 1, server 2, server 3, it says servers 1 and 2 saw a write and they incremented their version number to 2. They were not able to deliver the write to the third server, so they think that the third server still has version 1 of the file. Okay. So that's that partition there. This client wrote to a file, so these two servers updated the file and incremented their version number. That write could not be, since writes are broadcast, that write couldn't be sent to server 3 because there's a network partition. So each of them has a version number 221 for the file. Okay. Client B here also wrote to that file. Okay. And that file write was sent to server 3. And server 3 updated that file and it incremented its version number, its local version number, and it couldn't deliver the write to the other two. So it thinks that the version number is 112 and these two servers think is 221. This tells you that there is a concurrent write that has taken place and the two servers or the two server groups have a write-write conflict. Okay. So simply by comparing version numbers, and this is not a vector clock. Remember, this is just a simple integer that's incrementing versions as you write. You can figure out whether you have an older version of the file, whether the file was modified but some other servers did not see it, or if all the servers are connected, they will all have the same version number. Because every write will hit all the servers, they will all increment their version number, and all other servers will also know that they incremented the server version number. Okay. So this version number is a way by which servers can detect conflicts with one another, and the client will do the same thing. When the client or laptop disconnects, it will take a copy of all the files in its cache. It will have a version number, and when you write to it, it will increment that version number. So when you reconnect, you compare the local version numbers on the client with that of the server, and then you figure out whether the file was modified and you transmit. Okay, and I'll show you how this is done in just a moment. So here is basically how Coda works. Okay, there are three states for the server: this holding state, reintegration, and emulation state. Okay. So holding is a term that tells us that we are basically going to employ caching. A hold means you start copying data from the server to a local client and cache or create a hoard of data. Okay. So when you are in holding state, your client is connected to the server. You're simply asking what files should I download from the server, so that if this client is disconnected, the user has access to most of the data they normally work on. Okay. So you are basically in the connected mode, you're typically in holding state. Okay. Now once let's say the device goes out of this environment and you disconnect. You go on a plane ride or you drive off in a car or some such thing. Now you're disconnected from the network, then the device goes into what is called an emulation mode. Okay. In an emulation mode, the device pretends like it is connected to the server. So all applications transparently think that the data is still available to them, except that when they read or write, the reads and writes are hitting the local cache, not the real server. Okay. So you're in emulation mode. Okay. So applications don't see that the machine is disconnected from the network. It looks exactly the same from an application standpoint. Applications don't crash saying file not accessible or some such error. They continue to access data as if nothing has happened. Okay, so you continue to read and write data. Okay. Upon reconnection, you go into what is called a reintegration mode. The reintegration mode, for every file that you cache, you compare it with the server. You say, has the client modified it since the previous disconnection, or did the server see any updates from other clients? Okay, and then you can do pairwise exchange. This is like epidemic protocols, if you remember. Okay, you send your writes over to the server sends any more modifications it has seen to the client. If the file was modified at both ends, that's a write-write conflict. That's the same version number problem that you will see. Okay? In most cases, either the file will not be modified in either of the two places, or you may see only one of the two have seen modification. Okay, write-write conflicts are typically rare, but they will happen. If they happen, then you are basically going to flag that to the user saying there's a write-write conflict, figure something out. And then the user has to decide what to do with the conflict, how to merge the changes and things like that. Okay. So you'll go into reintegration mode. Once you've compared all the files and have copied all the changes, you'll again go into holding mode where you will ask, should I copy any more data? Did the user try to access some data that was not holded previously? Because you're constantly learning what the users are accessing, and you go into holding. So this process is going to keep continuing. Okay. So this is basically how Coda is going to work. Okay. So it basically gives you an illusion of an always connected file system, even though there will be periods where you're disconnected from the network. You take a copy of your data and you continue to use it. Okay. So that's the main new feature in Coda. Okay, the last point I'll make is the semantics that are provided. These are transactional semantics. Okay, so what that basically says is you are going to operate at a session level. Okay, and you will ensure that all of the changes are actually made to the file, and at the end you are going to flush them over. Okay, during the transaction you don't have to make any changes visible. Just as when I said you can have Unix semantics, you can have session semantics, you can have transactional semantics. In Coda, your transactional semantics. You have to ensure that operations are serializable, just as you have databases that serialize queries. When you have operations on a file, you want to ensure that they are serializable, which means that this application made all of these changes and this other application. If the applications conflict, you're going to get a write-write conflict, non-serializable changes, and then you are going to force a manual reconciliation. Because you are in disconnected mode, you have something that is slightly different from session semantics. You want to ensure serializability, or at least the designer decided that you want to ensure serializability of changes that are being made to the files. Maybe a bit stronger than what you need in a file system, because in most cases session semantics are okay but here you get transactional semantics for files. Any questions here? Okay, so because you are transactional semantics, you operate on a session level. The caches are going to send all of their changes when the file is closed or when you reconnect. Okay, so during those changes, you are not going to send any changes over to the server, or you're not going to send invalidation. You're going to wait until all of the changes have been made. You close the file, you flush. At that point, all of the changes are flushed over. Okay? What that also means is while some client is actually making modifications to the file, no other clients will see those changes because it's a transactional semantics. Okay? Writes are not immediately visible. They are only visible when you close the file. Okay? So if two clients are changing the file at the same time, they do not see each other's changes until they both close the file. Okay? Unlike in NFS where we said after you make a write, in 30 seconds those writes are sent over to the server. So even during the midst of making changes, other clients are going to see those changes. Here that is not the case. Okay? You'll only see it when the session ends. Okay? When you have a close, all of the invalidates of the changes are sent over. Okay? Different design decisions, okay, from NFS or Unix file systems. Any questions on this? Okay, so that's the first of the file systems. Okay, Coda, which as I said, very different design or philosophy, designed mostly for mobile devices. Yeah, today most of these ideas exist in some shape or form in many different systems. Okay, I already mentioned mail client, you probably use Dropbox, which uses similar philosophy. Okay? You have a local Dropbox cache where you can make changes. Okay, you could be disconnected, all the files are there. When you reconnect, there is a reconciliation protocol where you send changes to the server. Server may change, the Dropbox server may send you changes that it has received from other clients and so on. Okay. So these ideas live on in many different contexts even today. Okay. And Coda was a research project. Some of this code is open source, so you can use it, but it never actually became a commercial product. Okay. Next file system is XFS. Okay. This is also a research file system, meaning it's not a product that you can use. But again, the reason I put this up here is it has a very different philosophy from most other distributed file systems. Okay, X there, okay, the little x actually stands for no server. Okay, it's a cross saying this is a serverless file system. Okay. So think of this as there is no master copy in the system. Okay, it's like almost, no, I shouldn't say it's a peer-to-peer file system, but all machines are treated more or less identically. Any machine can store any data and provide those services to any other machine in the system. Okay. That's the philosophy. So it's a fully distributed file system that is serverless. Okay. The reason they wanted it to be serverless is they wanted to remove any centralized bottleneck. Okay. Even in a server distributed server oriented file system, the servers could become a bottleneck. There are lots of clients and a relatively small number of servers. There are lots of accesses, the servers will become the bottleneck. Here they said, why not use all of the machines in the network, okay, in some shape or form, and use their computational and storage resources to scale better. Okay, so it removes the bottleneck of a centralized client-server type file system. So X stands for no server, designed for high-speed environment. This picture probably doesn't convey much. All that you need to realize is there is no server, so you can store any data, which is file data or metadata on any machine. Okay, and there are two main ideas here. Okay. So first idea that is used in XFS is it basically distributes blocks of a file across machines. So thus far we have assumed that all the data for a single file is stored on a single machine. Okay. Here we have a notion called network striping. In network striping, if you have a server, a file with n blocks, the first block is stored on machine 1, the second block is stored on machine 2, third block is stored on machine 3, and so on. Okay. So file is chopped up into blocks. Okay. Blocks are spread across machines in the network. Okay. So to access a single file, you will now actually access multiple machines and get the relevant portions of the file from those machines. Okay. So this is referred to as network striping. Network striping itself is based on a concept called RAID, which is redundant array of independent disks. I'll talk about RAID, and then we'll come back to network striping so you have the background to understand what network striping or RAID does. So it is basically based on this notion of network striping. That's number one. And then the second thing it uses is what is called a log structured file system, which is another file system which was not a distributed file system. It was a centralized file system that was designed in Berkeley. Both of these systems were designed at Berkeley. Research came out of research project. So was RAID actually. So this file system combines all of these features. It uses RAID. Okay, but it uses software RAID and network striping, and it uses log structured organization. So I'm going to describe all of these concepts, and then we'll put it together in the context of XFS. The other thing it does is there is no centralized caching. Caching is not only distributed, it is cooperative. Okay? This is a term that we haven't encountered so far, but when we come back to the web, you will hear about cooperative caching. What a cooperative cache does is, when a read request comes in, you look at your local cache, see if the file is cached there. If not, rather than going to the master copy, you ask other nearby caches saying, do you have this data? Okay, so the caches themselves cooperate with one another to further reduce the load on the master copies of the file. Okay, so it uses cooperative caching for better performance. Okay, and we'll come back to that as well. So let us start with RAID first. I'm going to give a quick description of RAID in about 3 slides, and then we'll come back to XFS. Okay. So basic idea of RAID is to use multiple disks to store your data. Okay. So RAID is an acronym that stands for Redundant Array of Independent Disks. Okay. So you have a storage system that has multiple disks. Okay, for now, let's assume the disks are on the same machine. Okay? They don't have to be in XFS, they're actually disks on different machines, but assume that they're disks on the same machine. Okay? So you have multiple disks attached to a server. Now you want to use the storage space on this disk to store your files. The simplest thing is to not do anything and just use this as a separate disk. Okay? You construct a file system on this disk, and then one on this disk, and one on this disk. And each is a separate independent disk that stores its own files. Okay. This is referred to as just a bunch of disks. Okay, JBOD. It's an industry acronym, but let's just go with that one. Okay. Now what happens in this case is, if one of these disks fails, okay, this hardware failure, then all the data on that disk becomes unavailable. All the files are basically gone. You have to recover them from a backup somewhere. Okay. And furthermore, it is up to the user to decide what files go on what disks. Okay. If you store some files on this disk and those files are heavily accessed, this disk may actually have a heavier load than the other disk. Your load imbalances in your system. Okay. So whenever you have just a bunch of disks, you may have failures that make your data unavailable, and you will have load imbalances in the system because you don't know when you create the files how popular it is going to be, how many accesses it sees. Okay. RAID tries to address all of these limitations. Okay. It handles failures. It also handles this issue of load imbalances in the system. And the way it does this is through this notion of what is called striping. Okay. So we'll again put these 4 disks. Okay. Now let's say you want to store a file, okay, onto these disks. Rather than putting all the blocks of the files onto a single disk, you are going to actually stripe the blocks. That means block 1 is going to be stored on disk 1, block 2 goes here, block 3 goes here, block 4 goes here, and then you do round robin and you continue. Okay? So ith block is going to go on disk I mod n, where n is the number of disks. Okay. So what does this give us? The first thing it gives us is, when you access this file, you are going to send requests to individual disks. So you will get an n times speed up. You are getting the I/O power of all of the disks rather than a single disk. Okay, so you are going to get parallelism, okay, because now you are retrieving the blocks in parallel across multiple disks. Furthermore, your imbalance problem is gone. Every file is stored on all the disks. So if some files are more heavily accessed than the others, their load is spread across all of the disks, because to access any file, by definition, you need to send requests to all of the disks. Okay. So load imbalances are simply solved by striping the data across multiple disks. Okay, so this is called striping. Okay, it's a popular term or a popular concept in any distributed file system which we haven't yet encountered. This is the first time we've encountered it. Okay, so it basically takes your data and spreads it across this. You get parallelism, you reduce imbalances. Okay. Now that's a good part about striping. The bad part of striping is, again, if you go back to, let's say, single disk fail, let's say this disk went down. Okay. Now what has happened is, in the previous case, when that disk went down, only files that were stored on that disk become unavailable. All the files that were stored on the other disks were still available to you. Okay. If you employ striping, when this disk goes down, then 1/9 of all of your files become unavailable, because by definition all your files are no longer accessible, because portions of every file in your system has now become unavailable. Okay, so this is the downside of striping, is basically, unless you have additional techniques to deal with disk failures, by doing by trying to extract parallelism, we have made the reliability problem worse, because if any disk goes down, all the data stored on all the files, or all the data stored on all the disks, is no longer accessible. So you can't have every kth block of a file not being accessible. That just doesn't make any sense, right? So we have to now add some sort of reliability to the equation so that this problem doesn't cause for data to become unavailable. Okay. So we want to make it better than just a bunch of disks where at least a fraction of the files are unavailable. Here none of the data is available, and we'll look at that as well. Okay. So just to also look at this from another perspective. Okay, let's look at, just do an analysis of reliability. Typical disk reliability is either 50,000 hours or 100,000 hours. That's the lifetime of a disk. Right? When you buy a disk from, let's say you go to Best Buy or something, and you buy a disk, you look at its spec, it will say that mean time to failure, okay, which is the expected lifetime, is on the order of 50 to 100,000 hours, few years. Okay? And after a few years, then it will reach the end of its lifetime. Okay, that's around 6 years. Okay, now if you have an array with n disks, the probability of a failure is actually going to be the mean time to failure divided by the number of disks. Okay, because any disk can fail. As you have more components in your system, the probability that any one can fail keeps going up. So if you have actually, let's say, an array of 70 disks, you buy a server with 70 disks in it, the mean time to failure of any one disk, okay, drops from 6 years to 1 month. Okay, that means on an average, every month a disk is going to fail. Okay. So what that has also done is, as you increase the size of this array, the probability of failure has gone up. Okay, because the probability, if the disks fail independently, as you have more components, the probability of a failure keeps going up, that any one has failed. And furthermore, if any disk fails, all of your data also becomes unavailable. So it makes the problem worse from both perspectives. Okay, is that clear? So then the question is, you have striping, that's a good thing. You put in a lot of disks, so you get a very large storage system, that's also a good thing. But then the failure problem is worse. We need to fix that. Okay. The other thing I'll mention is, when you do striping from the outside, okay, what you basically see is an illusion of a single large disk. This is a larger logical disk that's a collection of individual physical disks. So you see a large volume whose capacity is n times the capacity of a single disk. So it looks like a much bigger logical disk from an application's perspective. So when you stripe, the presence of individual disks is hidden. You only see a larger volume that actually spans multiple physical disks from the outside. So now we'll come back to the failure problem and try to see how to address this. Okay? And this is where you actually see the R part of RAID. It says a redundant array of independent disks. So there has to be some redundancy of your data. Okay. Simplest form of redundancy is store a copy of every block somewhere else. Okay. This is called RAID 1 or mirroring. In RAID 1 or mirroring, for every disk in the system in your array, you have a backup disk. Okay. Every time you store a block on the primary, you are going to store a block on that mirror. So if the primary goes down, there's an exact copy on the mirror. Okay, so nothing from an outside perspective, all the data continues to be accessible. Okay, this is a very simple form of redundancy. It just says use mirroring for every block, store a copy of that block on a second disk. Okay. So the good part is, if any disk fails, you can access or the backup copy somewhere else. The bad part is you doubled your hardware cost. Okay? If you need to make, let's say, 100 terabyte system and each disk is a single terabyte, instead of buying 100 disks, you have to buy 200 disks because for every primary copy, you need a second disk. So you doubled your hardware cost in this case. Okay, so you get all the benefits, but your costs have gone up. Okay? So this is basically what is called mirroring. So now I'm going to show a slightly more sophisticated scheme that uses what is called parity. Okay, so this is RAID 5. Actually, RAID 4 works the same way. So in RAID 5, what happens is, so let's say you have 5 disk carry. Okay? Instead of having a single redundant disk for every primary disk, you have one redundant disk for a bunch of disks. Okay, so in this case, there are 4 primary disks and there's one redundant disk that's going to store some extra information that will allow us to deal with failures. This disk is often referred to as the parity disk. And the way it works is, you will basically have these blocks, D0, D1, D2, D3. You will take those blocks, you will compute some extra information, which is called the parity information, and store that parity block there. Okay, this block allows you to reconstruct any of these blocks if one of these disks were to go down. How it works, I'm going to show in just a moment. Okay, the basic concept is, you have what is called a parity group, which has k blocks. You compute the parity blocks as over these k blocks, and you store this extra information. Now, if you had simple mirroring, the parity was basically a copy, an exact copy of the original block. So there's one parity block which is a mirror of the original block. Here you have one parity block for every k blocks. Okay. So that what that also tells you is the extra hardware you need to get is 1 over k, not half. You are not doubled, but you only increase it by a fraction 1 over k. Because you need one disk in this case for every 4 disks. If the parity were computed over 10, then you need one extra disk for every 10 disks. Okay, so you can decide what the size of your parity group is. Let's see how this is going to work. So basically, the way the parity is computed is a simple XOR operation. Okay? You take D0, D1, D2, D3, you do an XOR over those blocks. Okay? That gives you the parity block which you store here. Okay? So you can ask, what does this achieve? So it's basically from the simple operation of XOR. What that says is, if this disk were to fail, okay, block D0 can simply be reconstructed as D1 XOR D2 XOR D3 XOR P. Okay, this is how XOR operation works. So basically, if A is B XOR C, okay, then you will see that then basically B is going to be A XOR C. Okay, which means if this was not available, you can take this and XOR them. That gives you back this. Or if this becomes unavailable, you will see C is B XOR A. That's basically how XOR works. This is binary XOR. So what that basically says is, if any of the components that were used to compute the XOR are unavailable, you can substitute the output of that XOR operation there and then XOR it with the rest that reconstruct the original. Okay? That's the basic law, very simple idea. That is uses binary logic from XOR. And so what that says is, now if this disk were to fail, everything continues to work transparently. If the application says, give me block D0, what the system will do internally, it will recover or retrieve D1, D2, D3 parity, compute an XOR that gives back whatever was stored at D0, and you hand back D0 as if you retrieved it from the original disk. Is that clear? So what that also says is, every time you write to any block of the parity group, you have to update the parity block as well. Okay, so writes are more complicated. If you write to block D0, you don't just go and overwrite whatever is stored in that block. You actually have to retrieve all of these blocks, okay? Recompute the parity, because the parity requires you to compute all of those blocks, and then write the parity and the return block. Okay? So a single write results in n reads plus 2 extra writes, one for the parity and one for the write. So writes are a lot more complicated in this system. Okay? Reads are straightforward. If there is no failure, a single read is a single read here. If there's a failure, a single read becomes the read of the entire parity group. But writes are always going to be more complicated, because you have to do what is called a read, modify, write. You read the parity group, okay, you modify the block that you're writing to, recompute the parity group or recompute the parity block, and you write back. Okay. batch writes are much more efficient in this case, because if you have to write 4 blocks at once, you could simply take the 4 blocks to be written, recompute a parity and just write them out. You don't have to read the original block. But small reads, which are individual blocks, are expensive. Okay, so this is what is referred to as RAID 5. I'm going to pause here for a second. Well, this is not RAID 5, this is actually RAID 4. I'll explain what RAID 5 is in just a moment. Any comments here? Yeah, go ahead. Oh, go ahead.
For the when you're doing a write, so you need to read every single other block, not just you can't compute it just from the parity block.
That's how you will actually do the parity computation. So if you had the parity block, that doesn't allow you to just do an update. You always have to basically re-XOR all of the blocks, which are these old blocks, the new block you're writing, and recompute. And that's how the XOR operation works. So there's no free lunch, more hard work. Yes?
The problem that you described here in terms of having to access the blocks on multiple disks, we could sort of do away with that by reducing the block size to some trivial size like 1 character. Then if you're writing 5 characters, 4 characters, then you obviously have to touch 4 disks in which you are not reading anything that is not necessary. Not touching anything that's not necessary.
Okay, so what is the problem that addresses, and I'll respond to that in just a moment. So you could write very small amounts of data. In fact, that's what RAID 3 does, but what does it do?
So instead of having to say if the blocks were 2K,
yeah,
then you have to read 2K, and assuming the disk bandwidth is slow, so you spend more time in reading 2K and then you just update 1 character, so you're wasting a lot of time. Yes. As opposed to make it like one character blocks.
Okay. So the point being made is, if you have the smaller block size, you won't have to read a lot of data. Okay, so this observation is true for any file system, not just RAID, because if you're, let's say, trying to read 1 byte, okay, the minimum granularity of reads or writes on any system is a block. Okay, that's how file systems work. They take a file, they chop it up into blocks, and you read or write blocks independent of what the application wants to read. You have to minimally read or write 1 block, even if it's 1 character. Okay. So the same thing is exacerbated in this scenario, because if you want to write 1 byte, simply you wanted to write 1 byte, this is a degenerate case to, let's say, block D0, you have to read the old block, okay, update just that 1 byte within that block. Now you have to read all these other blocks as well, because you have to recompute the parity, then you have to redo the parity and then write that information back. And what was being pointed out was, if you actually made the block size much smaller, in the degenerate case, you can actually make it 1 bit, not even a byte, you can make it 1 bit. And if you want to read or write 1 bit, so you're actually reading or writing 1 bit at a time. In fact, RAID 3 actually does 1 bit at a time. Okay, but the problem is, reading or writing 1 bit is, these are magnetic disks. Okay? There's an overhead to retrieving any data whatsoever, whether it's 1 byte, 1 bit, or 1 block, which is you have to actually perform a disk seek in order to get there. Okay? The disk is actually a platter, it's like a CD that's spinning. Right? So now when you want to try to read or write something, you have a disk head. Okay, think of a CD-ROM there or a DVD that's spinning, and there's a disk head. In order to read or write, the disk head has to actually move to the right place on the CD. Okay? And that's going to take you some latency. This is called a seek latency. This is a mechanical movement. Right? There's an actual head that's actually going to move back and forth. Okay? That mechanical movement incurs overheads of milliseconds. Once you're paid that price, if you just read 1 bit, okay, there's a huge amount of price to pay, and you read 1 bit. That's the useful work you did. Okay. So most file systems actually read or write blocks simply because they want to amortize the extra work of a disk seek and a rotational latency by doing some minimum amount of useful work, which is read an entire block. In fact, they try to make the block size as large as possible so that a disk seek overhead is spread across a large amount of actual transfer. Okay. Now, if you did that here, you will actually solve the problem of reading wasted data. But what you have is now your n disk seeks that are actually reading n bits, which makes the throughput or the performance of your system worse. Okay. So this is always going to be a trade-off in magnetic disks. Okay, the smaller the disk block size, the more efficient it is, because you don't have to waste your time reading any extra information the application doesn't care about. But smaller the block size, the worse your overall performance, because you have to at least perform one disk seek for every block or the small amount of data you read. Yeah, so you have to balance these trade-offs. Now, if you had solid state disks or SSDs, all of these problems go away. There is no disk C. Those are there is no moving part in an SSD. You simply address a block just as you address memory, and you can read that data instantaneously. In that case, you can make the block size small with no perceptible overhead on the system performance. Okay? But if you are traditional magnetic disk, this problem is going to really kill performance completely. Okay, so that's basically how to choose a block size. Yes. Okay. Question is, how does it handle scalability? So these are disks, not servers, but the same question is true of this. So if you add a disk, what happens? Right, with the system repartition. So that is up to how the system administrator wants to add disks. Okay? So what you could do is you could add 4 disks and then make them a separate parity group. Okay? In that case, no repartitioning is needed. This is one group, that's another group. They're independent. You can store whatever volumes you want. Or you could do what you said, you add a single disk and then you tell there's a disk array controller, you say add this disk to this parity group. Then in the background, it is going to start doing a lot of work. It's going to take D0, D1, D2, D3 and D4, because now you have one more disk, parity group has become bigger. It will restripe. Okay, all the data will be moved, it will restripe and repartition. Okay, but that's going to take order of hours or days, depending on how large the disks are for the repartitioning to complete. Okay, so you could do either of those two. The disk array controllers are capable of repartitioning, or the more common case is you don't add a disk to this parity group, you add an entire new bunch of disks and they make them their own group. Right. Okay. Now coming back to this scenario, if you have a single parity disk, which is what happens in RAID 4, you will see that the parity disk becomes a bottleneck. Okay. Any write on any of these disks also triggers an extra write on the parity disk. Because by definition, if you write to any of these blocks, you read the entire parity group and you write that block and the updated parity group. So this is showing you, these red boxes are showing if you write D0, you have to actually write eventually D0 in that parity block. If you write D5, you also write to that parity block. Right? So the load, the write load on the parity disk is the sum of the write load on all these individual disks. So that disk is getting the total union of all the writes on the other disk. So it's going to quickly become a bottleneck. So what RAID 5 does, this is RAID 4, it has a dedicated parity disk. What RAID 5 does is distributed parity. There is no real parity disk. Okay, as is shown here, the parity blocks are basically also spread across. So for that parity group, D0, D1, D2, D3, the 4th disk is the parity block. Okay. For the next 4 blocks, the parity block is here. Okay, the next 4, the parity block is here. So the parity block is itself distributed. So whenever you write, the parity writes are also now spread across all the disks. And the load is actually balanced. Okay. That is basically what RAID 5 is going to do for you. Okay, same as RAID 4, but no dedicated parity. Parity is also spread out. Okay, but the same concept is any disk fails. Okay, if you have to read any of these blocks, you are going to retrieve the entire remaining parity group and the parity block, do an XOR that's going to give you the failed block. Okay. This is how you are also going to reconstruct. You don't need a backup in case of RAID. You just simply pull out the old disk that is failed, you plug in a new disk, so then let's say this disk failed. So this is all blank block show up. Okay. Then the array controller goes into reconstruction mode where it starts reading the entire parity group. Okay. It reconstructs D8 and it writes it. And it will basically read P, D3, D4, D14, D15, do an XOR, reconstruct D12, write it. So after a few hours, all the data that was on the old disk that failed will reappear. Okay, at that point, you're back to normal operation. Okay, this is called RAID reconstruction. Okay, so you don't need to go to backup and bring the data back because all of the data needed to recover is already on the remaining disk. So you will have to basically reconstruct it on the fly. Is that clear? So this is RAID 4 and RAID 5. And now we can go back to, let's forget all the animation here.
Is there any way RAID can deal with 2 disk failures
Well, that's a good question. So I didn't actually say anything about failure handling in terms of multiple disk failure. So I should be clear. Okay, this scenario RAID 1 0, not RAID 0, RAID 1, RAID 4, RAID 5, it handles a single disk failure at a time. Okay, if one of these disks fail, you can still reconstruct. If two disks fail at the same time, you're out of luck. You actually are going to lose data. You need to go to backup and reconstruct because your redundancy level allows you to handle a single disk failure. So then that begs the question, what do you do if multiple disks fail? There are more sophisticated schemes. Okay, this is also referred to as an error correcting code. Parity is also called error correcting code. This parity allows you to tolerate single failure. If you want multiple failures, there are more sophisticated error correcting code that allow you to basically reconstruct if two of the blocks, K blocks, become unavailable. This basically says that 1 out of the K blocks, in this case 1 out of 4 become unavailable, you can reconstruct. So if you want 2 out of 4, you need to have more redundancy than this. Okay, so this will allow you to do what is called RAID 6 or RAID 1 plus 6, and there are many different schemes that allow you to do this. Okay? So the basic takeaway is they're more sophisticated schemes. In fact, if you look at some of the more recent research papers in this area, not just RAID, you can basically set K out of N blocks can fail. You can choose K, and that will tell you how much redundant information you have to maintain in order to reconstruct if only the remaining blocks are available. Okay, so K can go away at the same time. RAID allows that K to be 1 at the basic RAID. You can do more sophisticated versions, or you can go beyond RAID into all these error correcting codes and try to do more sophisticated failure handling. Okay. Cost is obviously going to be high. Okay. The cost of computing that error correcting codes and all of that goes up as you want to tolerate more and more failure. Storage overhead also goes up. Okay, so with that, we'll come back to now XFS, which is where we started. This was a brief detour just to understand what RAID does. So now that we have some background, we'll look at XFS. Okay, so remember I said XFS is a serverless file system. So what happens is you have servers. Okay, and these are not servers, rather we'll call them machines because they're serverless. Okay, and these machines have disks attached to them. Okay. XFS uses concept of a software RAID and network striping. Rather than striping blocks across disks that are connected to the same machine, you stripe blocks across disks that are connected to different machines. The same concept. So now you have a file. So you put the first block here. Okay. You put the second block here. If you're doing network striping RAID file, that block, then you have a parity here. Okay. I'm ignoring the parity for now. So you put the third block here, and then you will do round robin. These are now machines, independent machines and disks on independent machines. So you have spread your data across different machines. And you're going to do software RAID. What software RAID basically says is the file system will actually use a piece of software that figures out what data is on which disk, compute the parity block, and store it on yet another machine. Okay? So now you can have entire machines fail, not just disks fail, and still get back to your data. Okay, in RAID, the disks fail, you can actually, one disk fails, you can get your data, but let's say the machine itself goes down. All of the data becomes unavailable because all the disks are connected to that one machine. Okay. Here, that problem is gone because you have independent disks on independent machine. A machine can fail or a disk can fail, and you can still get to your data. Okay. Performance is going to be slower because parity computation is done in software. In most of the RAID type scenarios, you can actually buy a card, okay, like $100 or $200 RAID card, and it has an onboard controller that will do it for you with optimized hardware. So it's much more efficient than you write a piece of software that reads it, does it, and writes it back. So that impacts performance, yes.
What happens when two clients disconnect at the same time?
What's the question? What happens when
When
two clients disconnect at the same time? 2 clients disconnect in the same time. In XFS, you're asking? So we haven't even come to clients yet. These are just servers that are storing data. Are you asking if these two machines go away at the same time? Okay, so in this case, you can handle one failure. Okay, so one server can fail. If two servers fail, then your data becomes unavailable. If you want multiple failures, then you need more sophisticated error correcting code. That's always the case. Because if you're using software RAID, single disk failure, single machine failure. Two machines fail, data is gone.
So this is like, so these are essentially server entities, even though they're like, so the clients aren't going to be using their own disks as part of the system.
Yeah, so in XFS, the distinction between server and clients is gone. That's why it's serverless. That's the first thing to keep in mind. Okay, so having said that, you can actually have a trusted pool of mostly connected machines and a less trusted pool of machines that come and go. You don't want to store your critical data on a laptop that comes in the morning, goes home in the evening, and then you say that's a failure. If two people go home, then data becomes unavailable. That you don't want. So you want to have a trusted pool where you have machines that may be connected, let's say they're desktops that don't go away every evening. Okay, so those are the machines that will participate in storing this data, because certainly the disconnections are not failures, but they do make your data unavailable. So you can decide what is the pool of machines that over which you're going to do network striping. You don't want it on pools of machines or machines that disconnect frequently for that reason. Yes.
So if one machine were to read through a single file, it would mean for every block it would need network access it from some different machine and get it back.
Yes.
So so it's pretty expensive. So in which cases would XFS be used in other than Coda or something like that? Where is this more efficient?
So point being made is, if this laptop wanted to access a file, okay, because the file is striped, it has to send independent requests to these three machines, okay, and access, let's say the file is 3 blocks. Block 1 comes from here, block 2 comes from here, block 3 comes from here. Okay. And you are saying that is actually less efficient than if all these 3 disks were here, for instance, right? So now that's true to an extent that it's more complicated, that every file access requires you to go and read the data from many different machines that are on your network, not a single machine or a single server. Okay, having said that, the reason this network striping actually makes sense is that the networks have become much faster than the disks have. Okay. You've gone from 100 megabit to a gigabit to 10 gigabit Ethernet. Okay. So this network hop is becoming less and less expensive because this is a very fast link. Okay. The disks have not become faster at the same rate. The disks still spin at 32 or 3600 RPM or 7200 RPM. The disks are not spinning 10 times faster than they were spinning 10 years ago. The network has become 10 times faster. Okay? So because the network is very fast, the network hop is actually much small, very small as compared to the actual latency to access data from a disk. Okay? As a result, the fact that you have to go to multiple machines on a very fast network doesn't add to the latency of access. You are still limited by how fast your disks are. Now with SSDs, that problem is slightly different, because SSDs are made an order of magnitude jump in the speed. The disks no longer spin. SSDs are very fast disks. They don't have any moving part. But if you're magnetic disks, this is not a problem, simply because if you had a slow network, this would be a problem. This is all system trade-offs. Slow network, fast disks, don't do this. Fast network, slow disk, this makes perfect sense. You are using I/O parallelism. In fact, you are going to get better performance. So these are all trade-offs that are made based on how systems are evolved. Okay, so that's XFS. Now the second part of XFS, which I didn't mention, is what is called a log structured organization, or LF. It derives from another file system called a log structured file system. Okay, and I'll talk about log structured file system, and then we'll put both of those things together. Okay, so in XFS, what happens is a file is a log, and the log is striped across a network. Okay, so I just talked about striping, but I didn't talk about log structured file system. So this is another file system that you should know about, and we'll ask why this makes sense. So here is basically a simple scenario of how a log structured file system works. Okay. So you basically have your disk. Okay. Let's say you have a server, and then you have RAM, and you have a disk. So now this file system was also designed in the maybe early 90s, almost 20 years old. And the motivation for the design of this file system was as follows. Okay, so let's say your applications that are sending read and write requests, okay, to your server. Okay. Let's say assume that there is no server, it's a local file system, just for simplicity. So applications read and write their data. Okay. Typically, most file systems store their data on disk and they have a in-memory cache for optimization, performance optimization. So whenever a read hits the OS, the OS is going to look in the cache, which is in RAM. If the block is already cached, you send that block to the application. If the block is not cached, you actually go to the disk, retrieve it, store a copy in the cache, and then return a copy to the application. This is how most file systems will work. Any file system. It has a cache that is in memory that speeds up access to the block, frequently accessed block. So by caching frequently accessed blocks, you get better performance. Okay. Now, with that in mind, if you look at the traffic that is coming into the OS, the read and write traffic, and then see what part of the traffic gets filtered in the cache and what actually hits the disk, you will actually see some interesting trends. So first, let's assume there are equal number of reads and writes coming into the system. Okay? And some of those I/O requests are actually filtered out by the cache. Their cache hits. Okay, so they never hit the disk. They are actually serviced directly from the cache. Then you see what fraction of those are actually not serviced from the cache. What are the ones that always have to go to disk? Those are all going to be the cache misses. Okay, all cache misses are going to hit the disk. Right? Now, if you actually think about it, you will realize that a large fraction of the cache misses are always going to be write requests. Okay? Because by definition, when you write, you may first write to the cache, but you have to put a copy eventually to the disk. Because if your machine crashes, memory contents go away. So you have to make it persistent. Every write has to always trickle down to the disk. Okay, reads, on the other hand, if you service them from the cache, there's never going to be traffic seen by the disk. Okay? So the observation that the people who designed this system made is that once even if equal number of reads and writes are hitting your OS, okay, the disk traffic is predominantly writes with few reads. The reads are the few occasional cache misses, but once the data comes to the cache, then all subsequent reads to the files are again serviced from the cache. Okay, so is that clear? So if you put a large cache in front of a disk, the cache will filter out most of the frequently accessed files, okay? And what is actually going to be seen by the disk is a large fraction of writes. So that is going to ask the question, if your actual disk traffic is predominantly write based, how should you redesign your file system to optimize for this scenario? Okay, is that clear? So if you think of a file system that mostly sees write requests, occasionally sees read requests, the remaining read requests are handled from the cache. What should you do to your file system to optimize for this scenario? Okay, that is basically the observation that led to the design of block structured file system. Okay. I'll tell you what they did and then you can see if it makes sense. Okay, the first thing that you can do is, this is a magnetic disk. Okay, as I said, every time you write, you are going to incur a disk seek. Okay, if you write to a particular location, you have to move the disk head to that location, because this is, think of a disk like a CD or a DVD. You want to write to a particular location, move the disk head there and you write. Okay, the disk head is all wasted overhead. No useful work is being done when the disk head is moving to the place where it actually needs to perform the write. Okay. So the single best thing you can do is eliminate disk seeks or reduce them dramatically. Okay. In fact, all file system optimizations, whether they're log structured or not, are simply designed to reduce the overhead of disk seeks. Whatever you can do to reduce disk seek, the better your performance will be. Okay. The less disk head is moving, the more you can do useful work. The higher throughput you're going to get. Okay. So now you can ask, what is the simplest thing you can do to reduce disk seeks altogether? Okay. So if you could continuously keep writing to the next location, okay, you write block I. Next write comes, you write block I plus 1. Next write comes, you write block I plus 2. Okay. So you're just writing sequentially. There's no need to move the disk anywhere, because you know that the next write is actually going to hit. When it hits, you're going to write to the next block. Right? That's the simplest thing you can do, and now you don't have to move the disk head all over the place. Right? And that is basically what log structured organization in fact does. It writes in an append only mode. It says, whenever I write, I'm going to write to the next location. I'm not going to move my diskette to some random location and write there. Okay? So I'm simply going to write sequentially. Okay? So basically this is your log. Okay? That's why it's called a log. Always append to the log. I'm going to keep writing, okay, to the end of the log. Okay, so that's the basic idea. Now that does bring up some interesting questions, saying you had a file had 3 blocks, A, B, and C. Okay, let's say A is stored here in the block, and you wrote B, you stored it here, and then you wrote C, you stored it there, and there are some other blocks that got written from some other files. All the files are being written as a single log. It's not a log per file. You take all the writes, you just write them in a log. Okay? So a file has 3 blocks, A, B, and C. A is written in this location, B here, and C here. Now you go and update B. What should you do? Okay, write a new copy, yes.
I was going to say, I think you could just keep adding like segments of B after C.
Okay. So the old way, in the old file system, if you wrote B, you are going to go back and overwrite B. Okay, that's how file systems work. Once you allocate space, if you make changes to the data, you go and overwrite the old data. Okay. That would mean if the disk head is here, you would have to go back there and write B prime. Okay. That's disk head movement. Okay. You don't want to do that. Okay. So what are you going to do? You are going to simply keep writing B here. So the new copy of B has been written here. Somehow you have to mark that old copy is invalid. Okay. That entry in the log is invalid. So long as you can do these two things, you don't need to move the disk head at all. You keep writing. As the data is getting overwritten, you write new copies to the end of the block and you mark the old copies as invalid. Okay? So this is basically how log structured organization is going to work. Okay? Now eventually, okay, because you do this, you are going to reach the end of the disk, okay? But you are not going to be out of space because there are lots of data here that you marked as invalid. So you are going to recycle and try to write to those blocks. Okay? But since you don't want to write to random locations in the middle of the log, okay, you have to do garbage collection. Okay, so the way garbage collection works is, although I said you just write sequentially, you don't do it exactly this way. What you do is you assume that you have a sequence of segments, okay, in your log. Okay, think of these pages in a diary. Okay, you're just writing sequentially. So you keep writing. And then as data is overwritten, you basically, some of these entries in your segment become invalid. Okay? And then you basically, after a while, after you used up all the segments, you have to go and do some garbage collection. You see, what are segments that have a great fraction of invalid entries? Okay? When you garbage collect, let's say of the 10 blocks, only 2 are valid, 8 are invalid. Then what you will do is you will take those 2 and you will write them to some end of your log and you will mark this entire segment as empty, available to be rewritten. Okay? So the next time you cycle back in the log, you'll basically write sequentially in this segment. You'll find the next empty segment, write sequentially in that segment. So it's sequential at a segment granularity, not sequential at a disk granularity. Segments can be large. Okay? Unlike blocks that are 1 kilobyte, you can have large segments. Okay? But periodically, you have to do garbage collection. This is the single biggest disadvantage of log structured file system, is you have to garbage collect because there's all these invalid entries that are popped in. And since you're trying to write sequentially, you can't go and write to holes. Okay? You want to write sequentially. So you have to do garbage collection and then you have to empty an entire segment. So you can write sequentially through that segment. Okay? So basically, if you have log structured file system, you will see periodically your disk will start spinning. Okay, you are not doing anything. You're just sitting there and your disk starts churning away. Okay, system performance tanks. Okay, because now you're trying to write, there's a lot of copying going on and garbage collection going on. So there's a lot of extra work that you have to do in terms of garbage collection just to allow you to get this right performance. Garbage collection is infrequent operation, but every once in a while when the system starts it, you will basically, until it has reclaimed some of these segments, you are going to see bad performance. This is the only reason why these log structured file systems have not taken off. Okay, they are available, they have been coded up, and the performance of garbage collection people still don't like. This is extra data copying. In garbage collection, simply copying valid data into new segments and freeing up old data. Yeah, that's an extra overhead. which is why this doesn't actually work. Okay, meaning it works, but it doesn't work for commercial products. People don't want your system to be just doing something in the background while there's no useful activity or system's closed down. Okay. Nevertheless, very interesting idea. It's trying to handle this case where your traffic is predominantly write only. If the traffic had reads and writes, this would not make sense. Remember that. You may be writing sequentially to the log, but the reads are still going to be random. You can't force the read to be the next the thing in the log. The reads are whatever the application wants to read, and the diskette is moving back and forth. Okay? This only works if you're predominantly write traffic with infrequent reads, which is what happens if you have a big cache. Okay? If you didn't have this cache, none of this would make sense, because if the diskette is moving, then why bother? You go and overwrite the block anyway. Why you want to write it at the end of the day? Okay? So those are some things that log structured file systems do. Okay, and now coming back to XFS, what it does is it combines the two. Okay? Every file is a log. Okay? And then furthermore, the log is striped across machines in the system. So that is striping, that's a log. So you always write to the end. So within each disk, you're going to write sequentially. Okay? And then across disk, you're going to stripe the log. Okay? So that you get parallelism and you get fault tolerance and so on and so forth. So there's no server. You have a trusted pool of machines that can all pool their storage together, okay, to give you good performance. So a file is spread across multiple machines. Okay. It is stored in a log organization to get you good write performance. And furthermore, you are actually exploiting both the storage space and the I/O bandwidth of disks on lots of different machines in your network. Okay. So you put all these concepts together, you have this system called XFS. Somewhat complicated system, but gives very good performance because it is done away with central servers and so on. Okay, so I have two more slides and then we will end. So HDFS is yet another file system. This is a file system that is designed for Hadoop. If any of you have used Hadoop or MapReduce, you would have encountered HDFS. If you haven't, it doesn't matter. Okay, I'll just talk about what it does. Okay. So this file system is optimized for batch operations, not interactive use. It is not meant for I open up my code in my browser, I edit and I save. That's not the kind of file system this is. This is actually a file system that is designed to store very large data sets that you are going to retrieve in batch mode to do some computation. Okay. You have a very lots of data, let's say lots of data, you want to read it all, do some computation and then write some intermediate data. Okay. So it is designed for batch optimized for batch operations, not interactive. Everything we have done so far is interactive. Okay? Because it is batch mode, there are different design decisions here. Okay? So you want high throughput. You don't care about low latency access to a single block. What you want is very high throughput access to lots of blocks, because your applications, higher level batch application, in this case is Hadoop, that's going to read lots of data all at once. Okay? So you want to get high throughput, which you will achieve through parallelism. Okay? Furthermore, since you have lots of data, you will have to have lots of disks. You can't store all of that data on one disk. So you need fault tolerance just as you had in RAID. Okay, otherwise, you are going to have disk failures, cause other failures. Now, HDFS doesn't use any of the RAID concepts for fault tolerance. It uses simple mirroring like concept. It stores 3 or copies of every block by default. That choice of whether it's 3 or 4 or 2 is configurable. So every block is replicated k times, okay, because the assumption that disks are cheap. You can buy 1 terabyte for $100. Why spend all your time doing parity? Simply store k copies and be done. Okay, so very simple design decision. So fault tolerance by storing k copies. Okay, your batch processing, so you have to basically stripe, not stripe, but spread the blocks across multiple disks so you get high parallelism. Okay, and it is designed to scale to lots of nodes. Consistency model is very trivial. Right? It is assumed that data sets, because this is batch operation, not interactive use, you're not going to retrieve some data set and modify the 1 millionth record and write it back. You just read the whole thing, process it, produce some output. Okay, that's the typical mode. So you assume that this is write once, read many. Once you create some data, you typically don't modify it after you write. This is the assumption. Okay, so you have basically you just store dump data. You process it and you create some other data. You don't go and start modifying something in the mid. You can append. Right? So append is allowed, But once you store, typically the assumption is you don't want to change. You can add to the data set by storing new data that may occur, but you don't go and start modifying things that have already been written. So very simple consistency. Lot of the complexity of distributed file systems is gone because you assume files don't change; they can only be appended to. Okay, so nothing much has to be done in that case. Okay. So when you write, you create k copies and then you're done, and you keep appending to the file. Okay, and then the last thing here is the system is assuming that whenever possible, because the amount of data is very large, whenever possible, you move the computation to where the data is rather than moving the data to where the computation is. So rather than reading over a network, if the higher level batch application intelligently say, this is where this part of the data is, so I'm going to actually send the job there and do it locally, this gives you the best performance. Okay. Doesn't mean that all of it has to be done that way. Remove computation closer to the data, you will get better performance. Okay. So one more slide here on HDFS. So having said all that, this is a picture that shows you how HDFS works. The main principle here is to separate metadata servers from data servers. Okay? So think of it as there are two types of nodes. Nodes that store metadata, which is simply information about where the actual data is stored, and nodes that actually store the data. Okay? In this case, the blue node is a metadata node. If you say, give me file X, it has information about where the blocks of the files are on the data nodes. Okay? The yellow nodes are the data nodes. They actually store blocks of the files. Furthermore, they'll replicate blocks of each file. Okay? So the information about where each replica is stored is also on the metadata node. Okay? This separation of metadata servers from data servers is a general principle that many high-performance file systems use today. If you buy very high scalable file system, this is a common principle. Even HDFS employs it, but it is by no means unique to HDFS. So that principle is very common in very large distributed files. The metadata nodes that store information about data nodes. Okay, so this separation actually helps you get better performance. When you want to retrieve a file, you first go to the metadata server, it tells you where the blocks are, then you go to the data servers and retrieve those blocks. And that's basically how it works. And the last thing I should say is both the block size and the replication factor is configurable. Okay? Typical default replication factor is 3. For every block, you make 3 copies, put it on 3 independent machines. Okay, so if any machine goes down, this goes down, you have 2 more copies. So here you can at least handle 2 failures if you have 3 copies, okay, automatically. Okay. And the other thing is, because this is batch operation, the block size is typically large. Okay. You don't use 4 kilobyte block size as you use in typical file system. You use block size that may be megabytes in size, because you read lots of data, you process it. The larger your block size, the more you can amortize that single seek. Okay, you make one seek, let's say you read 64 megabytes of data all at once. Okay. So that has amortized your seek substantially, so you get very high performance. Okay. This won't work if you have interactive application. If you are reading a source code and you make one line change, you don't have to read 64 megabytes just to make that change. But your application that's reading a terabyte data set to process it, like your MapReduce, this makes good sense. So this is a different philosophy designed for batch application, not interactive application. So completely different set of design principles. Any questions here? Yes.
So the point that you made in the last slide where you take the computation to the data.
Yeah.
So you're assuming a model where there are like servers, each of the server is associated with a disk.
Yes.
As opposed to, I was under the impression that in a data center, all the disks are bundled together into a storage area network and the servers are bundled together. So probably
good point. So the point being made is, I said you can move computation to the data. This assumes that the nodes that store the data can also perform computation. If you take a traditional data center architecture, the storage nodes or the storage servers are separate from the compute nodes. There's a file system that could be a storage area network or a distributed file system that's stored on some machines, and other machines connect to that machines and read and write data. In that scenario, your storage system and your compute system are separate. You can't really move the data and the computation. The data always moves to the computation. Nodes retrieve data from the server and operate on it. Okay. HDFS is designed for MapReduce, where it is assumed that your commodity machines and you're using the disks on commodity machines for the storage and the CPUs on the same machines to do the computation. Okay, That's how MapReduce work. So in the scenario where the compute nodes and the storage nodes are one and the same, okay, you can do this. And in HDFS and Hadoop, you can do that. In a general data center architecture, you cannot do that. Okay, so this is designed very specifically for Hadoop, but you can use the file system for other purposes as well. Okay, so in this case, the nodes here which are on the rack, these nodes can also perform computation. Okay, that's the assumption. Otherwise, that observation will not hold. Okay. Last slide is on object storage systems. So this is yet another distributed storage system. Here, rather than storing data as files, you store them as containers of arbitrary sizes called objects. Objects have handles. You use the handle to get to your object. Okay. How the system stores the object, where it stores it, what disks, what machines is transparent to you. Okay. You will encounter object storage system when you do the cloud computing homework that I've just put up. Okay. Amazon has something called an S3 service, simple storage service. That's an object-based storage system. You are going to create something called buckets. In buckets, you are going to store objects. And you will get an HTTP name to get to your data. They won't have file names anymore. They'll have URLs. You use HTTP to retrieve data. Okay. You're going to use HTTP operations such as get and put to or delete to actually manipulate the blocks or manipulate the objects. Okay. So files have blocks. Objects are no such abstraction. You actually get entire objects at a time. That's the granularity at which you're going to retrieve it. Okay. So you can actually use an object-based system and layer a file system on top, or you can simply deal with objects. Okay. Now this kind of systems have become very popular in two scenarios. Okay. One is for backup purposes. So object storage systems are very popular for backups. Okay. You can take an entire dump of a file system, make that one large object and put it into an object storage system. So that's one way to do sort of archival. In that case, you can do internal optimization like data deduplication. Because you're not storing individual blocks, you're storing entire objects. There is a great deal of flexibility of how you actually store that data in the object onto file. You have two blocks that are the same, rather than storing two copies, you store one. So two files that are same, you can also store one. Okay, so all these optimizations can be performed. Okay. The other use case is cloud storage. This is what I was just mentioning. And if you have a large disk-based images, this is another popular way by storing entire images or any kind of data for that matter onto a cloud storage system. Okay. So you don't give them file names, you give them URLs. Okay. And you access them using that URL, as you will see when you do the cloud assignment. Okay. So this is the most recent evolution of storage system, is object-based stores and not file stores. Okay. So this is also something that you should know, so I thought I'll have at least one slide on it. Okay. So with that, we have run out of time, so we'll stop here and continue on Wednesday.